there's a lot of showing code here, so I'm probably going to be sitting down hiding behind the computer most of the time, but let's see how we can do this. So we're going to talk about neural networks, and the biggest problem about neural networks is this. It's a boatload of math. When you try to learn neural networks, you start reading about it, then you go to a page that is like a whole page of formulas, and then you scroll down and it's another whole page of formulas, and you do that 20 times, close the tab, never look at it again. So we're going to learn how neural networks, what they are, how they work, how we can implement one, but without all of that crazy, Greek characters and arrows and curves and whatever the hell they are. So the main premise of this talk is that neural networks, there are some complicated parts, but they're not like the mostest complicated thing in your life. The problem is math notation, so we're going to do it without math notation. I'm just going to give you a quick intro of what a neural network actually is, and just so we know what we're talking about as I show you in practice. So a neural network is a predictor system. It's a thing that you give it some input, then it does magic, and it gives you an output. And that magic is supposed to be accurate, and that magic is supposed to learn how to do better. So we're going to have a way to say, okay, how wrong was this prediction? Then we're going to have a way to say, for every little thing inside my neural network that I changed, how much is my output going to change? And is that going to make the how wrong I am smaller? Because that's our goal. So we're going to have cycles of learning where every time we do a cycle, it's called an epoch in the neural network terminology. Every time we do a cycle, the amount of wrong that I am is going to be slightly smaller. That's the whole goal. And the way a neural network is structured is we have neurons, which are like the atomic parts of a neural network. Then we have layers, which is a bunch of neurons that share the same input. And then we have the actual neural network, which is a bunch of layers made of neurons that communicate information down the network, and hopefully that's going to make accurate predictions, because at the end of the day, it's still a predictor, the thing that we're working with. So now I'm going to sit down and let's get to it. So first we have a predictor, which is something with an input, does some magic, and gives me an output. So what does this look like in code? Can you see this well? Yeah. Okay, so it's simple, easy. You can, how it predicts, I don't care. It's just, a thing that has some inputs and it executes some code and gives me some output. The way we're going to do this on a neural network is we're going to have neurons. So what is a neuron at the end of the day? It's a thing that you give it an arbitrary number of inputs. It's going to multiply every input by a weight. And you can think of a weight as being like an opinion, a point of view, something like that. It's just going to say, my third input is going to be multiplied by 0.5 because. That's just how it works. At the end of the day, at the end of this process, I'm going to sum up all of the values. So if I have 3 inputs, I multiply it by 3 weights. I'm going to have 3 outputs. I add them all together, and then I add a bias at the end. And I'm going to explain what the bias is soon. And then I need a way to actually let's look at what this looks like first. So a neuron is a bunch of weights and a bias. To create a new neuron, I just make here a slice of floats. The amount of items in the slice is going to be the amount of inputs that I have, and these are going to be my weights. Then I have the bias, that's just a single value, and they're all going to be just random stuff, because I don't want a neural network to start everything at 0, because then all neurons would be the same and it would not make sense. So I just do random values to make some fun. And how to predict with the system is what I just explained. So we take every input, multiply by a weight. I sum all of this into a single value, and then I add the bias at the end, and that is my prediction. Something else that I need is to be able to calculate loss. Now, to do that, I'm going to take a data set, for example, a list of cars, and what's the mileage, how old is the car, and then how much it costs. I put the inputs in my predictor. I take whatever output my predictor did, and then I say, okay, the predicted output minus the actual correct output is how wrong you are. So this is what we're going to do. And this is we're going to use a mean square error function. And so this is what I just told you. The actual output minus the predicted output is how wrong I am. But we're going to square this because if we don't, then if I have an error of 2 for one thing and an error of minus 2 for the other thing, then my system's going to think that it's perfect because the error is 0 because they cancel each other. So that's not going to work. So we just square everything and then divide by the number of items, and that's my mean square error. So my goal throughout this whole process is going to be to make the output of this function as small as possible. So I have a little app here. It looks kind of squished here. So this is a little application. It has 4 services that are containers. One is the neural network, which is the code that we're working on. The other is a normalization service, which is going to take inputs. For example, why is this not working? For example, my car can be 9,000 kilometers of mileage, or it can have 200,000, and the normalization service is just going to make everything between 0 and 1, something like that, which don't need to talk about really, but just explaining how this app works. And then the front end, the console are, how you're seeing things. The console just looks like this, and the front end takes all the services together and tosses them in in the front end, I guess. Then I'm using Garden here, which is Kubernetes orchestrator, so that every time I make a change to my code, it's going to rebuild my container, redeploy my container, and run a different kind of neural network as we make the changes. So this first network that ran here is what we have seen on the code so far, and it doesn't have epochs because it doesn't know how training works yet. It just made a single prediction. It's wrong by this factor. And basically, that's all I have so far. So this is terrible because it's telling me, for example, that a 12-year-old car should cost 96,000 euros, which it's kind of a bit too much, I guess. And so we need to be able to train this network so that the results get better over time. So how does training works? First, I need to know, I already know how wrong I am from the loss function. Now I need to know how changing every weight in my neuron is going to affect the output. And to do that, I need to look at every little thing and say, okay, if I add 1 here, by how much is the output going to change? By what factor? So let me show you here, somewhere. Nope, not here. Here, training, neuron. So for example, actually, I have this in a slide. Okay. So for example, my bias. The bias is added at the end of the calculations of my neuron. And it's just, I take the number and I add it. That's the only transformation I do. So if suddenly my bias increases by 10, how much is my output going to change by? 10. So it's a factor of 1, because that's all I'm doing. On the weight, if I change my weight by, if I double my weight, for example, then I need to the amount that the output of the network is going to change is going to be multiplied by my input, because the weights multiply the inputs. So if I change the weight by 0.5, the amount that the output of the neuron is going to change is 0.5 times whatever that value is going to be multiplying. So since the weight multiplied the input and the input multiplies the weights, then the gradient for the input is the weight and the gradient for the weight is the input. Because each multiply, you all look confused. So I have 2 things that one multiply the other. So if I change one thing, by how much is the result going to change? By the other thing. Because one multiplied the other, so changes in one are multiplied by the other thing. Okay, I think it makes sense now. So this is what I have here. So I'm simply saying, okay, the gradient for the bias is always 1, because that's how it's going to change. And then the gradient for my weight is my input, and the gradient for my input is my weight. So this is the thing I just said. You look confused again. Let's skip this part. So let me just take this here and put it on the main file. Now, something else we need to know is, okay, I know how wrong I am, and I know how everything that I change is going to affect the output, so now I can do training. The way this works is I just take the loss function, the how wrong I am, I multiply by the gradient, and I multiply by the learning rate. So the first 2 parts here, I think you already understand-ish. About how we got these values and what they do, and then we have the learning rate. So why do we have a learning rate, and what is a learning rate? A learning rate simply means that we're not going to make big jumps in the values. So I'm not going to take a weight that is, I don't know, 1 and make it 10 because that's going to be the magic value. No, we're going to jump in little increments. And the reason we're doing that is because when we do this process, we're going to have a gradient for the loss function, which, like we just said, the gradient for simpler things, if I add 10 to my bias, it's going to change by 10 my output. This is basically saying that, okay, if I want to change my weight by 10, what do I change in the main value? We have this 2 ways. So I do a prediction to take the input and get me the output, and I use the gradients to know if I want to change the output, how do I change the first thing. When we do the gradient function for when you look at the gradient for the loss function, which tells me how wrong I am, that function is like this. It's I forget the math name for wobbly things. What? Yeah, parabola. If this is wrong, it's her fault. So the thing about this is the gradient, it only works for a single point. Like if I look at the gradient in different points of the curve, it is different. It's a different line. So I can't just take an arbitrary point and say, okay, how do I change this to make the whole output of the function 0? I can't do this. There's no math that can give me this. But what I can do is, if I'm here, what is the gradient for the next little point right over and the next little point right over? So that's what the learning rate is for. So I take small steps instead of trying to make big jumps, because the big jumps are going to be wrong, and we know that for a fact. The small steps are going to be slightly wrong, so that's better. And if I make steps too big, I kind of end up just jumping from one side to the other of this function, and I never reach the point where the error is the smallest. So let's look at all of this in code, because I think it's easier to explain than just theory. So I have a neuron. Okay, the gradients, we saw the loss function. Okay, this is how we're going to calculate the gradients for the loss function, which is if I change something somewhere in my network, by how much is the output going to change, the output of the loss function going to change. And the thing is, we want the loss function to give me the smallest possible result. So the formula that made this function, that brought this function here, I don't know. I don't understand. It's a thing like, what is a square root? I know what a square root is. I know what it is for. Do I know the best algorithm to calculate the square root? No, and I don't care. So this is the same situation. It's just some mathematician said this was right. I copied the thing. It's there. It works. I don't care. And then to do the actual training, I call my gradient descent, which is the name of this process here. It's going to find out the mean square error gradients, which is the loss function gradients. This is going to use the gradients of my neurons in turn. So, long story short, I know how every little change that I do is going to change the output. I want the output of the loss function to be the smallest as possible. So I'm just multiplying all the things, and theoretically, once I do this, once I add the things to my parameters, I'm going to be changing the weights in the neural network so that every little change that I make is going to make the loss of my network slightly smaller. So I'm going to save this, and we're just going to look at how the graph is going to be a bit different now. And it is redeploying, rebuilding, all of that stuff. And okay, so now it's going here. You can see that it basically learned all that it could in one fell swoop. And the predictions are off, but they're not horrible. So it learned what it could. But this is still very linear, because all my I just have one neuron here, and all my neuron is doing is, multiplying some stuff, adding a bias. So it's not really complex. And what I need to do is two things now. We need to have a layer, which is we need to have the scaffolding so we can work with multiple neurons at a time. And we need to make the output of my neuron nonlinear, because if it's linear, it doesn't work for lots of things. For example, if I'm trying to predict the growth of a population, that doesn't work if my graph is linear. If I'm trying to predict a growth of bacteria in a Petri dish, that also doesn't work because it's not linear. And for example, if I have a car and it's a 2013 model when they redesigned things, and now the car's prettier and suddenly more expensive, but it's more expensive for some reason that does not directly relate to mileage, for example. If my processing is linear, I cannot make that work. I need something that's going to be weird. And so this is a this is a sigmoid function that you see here. It's going to take whatever you throw at it. It's going to give you an output between 1 and 0. And there it is. And the way it's going to do so is in a nonlinear fashion. And that's kind of what we want. So the fact that it is, there are many functions that we can use as activation functions. Sigmoid is one of them. Everyone hates it, but it's the simplest, so we're going to go with that. And this explains why we need bias in our neuron, because there are parts of this curve that are not really relevant. For example, if I look at the very beginning or at the very end, it's kind of boring. Things don't change much. So I want my frame to be in the part that is changing, basically. And the bias allows me to shift where my frame is. And then the layer is, like I said before, a neuron layer is a bunch of neurons that share the same input. So we're going to add that to the code as well. And then we're going to get to the network soon. So what changes here? My layer. OK, a layer is a slice of neurons. It has an activation function. To create a layer, I just create a bunch of neurons. And they're going to share the same input. This is mostly boilerplate. The prediction for a layer is going to be, I'm going to do the prediction for every neuron. I'm going to take this prediction, I'm going to run it through my activation function so that the actual output of the neuron is nonlinear. It's not just a predictable thing that I just multiply and add. It's going to be, crazy stuff. And then I add all of this to a slice, and those are going to be my results. The gradients are similar fashion. I'm going to make a prediction. So the prediction gives me basically 1 point in that parabola graph. I'm going to have to see the gradient of my activation function at that point. And then I'm going to multiply that by the gradients of my neuron. And that is going to be the gradients of the... Basically, I'm taking the gradient of every neuron and multiplying it by the gradient of the activation function at that point. And then I'm saving all of those values for every neuron in a slice, and that is the gradients for my neuron, for my layer. There's also, here's the activation function. So here's the function for the sigmoid. The sigmoid, just to recap, is this wobbly thing here. And this is the gradient for the sigmoid. So I always need to know whatever function I have in a neural network, I need to know how to execute the function and how to basically infer the result from the end. So, OK, if I want this result to be higher or smaller, what do I need to change? And then the gradient gives me that. So I'm going to save this. We're going to look at how it runs, the curve here. So it's redeploying. And now, because there's an activation function, because things aren't so linear, and we're actually going to have the gradient for the loss function, you see that there's an actual learning process happening here. So it tapers out after a few cycles, but you can see that, and the results are terrible. I probably messed something up in the implementation. But you can see that there was a learning curve. And this learning curve is basically saying, OK, I have that graph of the loss function, and I'm slowly going towards the minimum point where the loss is smaller. So the implementation here is not too good, but it's probably some bug, I don't know. But the concept is that. And that brings us to the most complicated bit, which is how do we turn this into an actual network? Because what we saw so far was basically, add stuff, multiply stuff, take some gradient function that you copied from Wikipedia and run this through that, and multiply things again. And now comes the actual tricky part of a neural network. To make a prediction with a network, and a network is just a bunch of layers, one in front of the other. To make a prediction, it's pretty simple. You just, the first layer is going to have as input, whatever my data set has. The second layer is going to have as input whatever the layer before gave me. And, the last layer here, the output layer, is also going to have as input all the things that came from the layer before. So this is easy. Doing the forward pass on a neural network is straightforward. This is like 4 lines of code. I'm actually going to show you right now. It's here. Network. Where are you? Predict. So the first time I run this, I use the input from my data set, and then every time I run this afterwards, I take the prediction from the previous layer and use it as input for the next layer. So it's that simple. Now, what is it that is really hard about neural networks? Is calculating the gradient, because, okay, I know I have one neuron here, and I know that if I change one thing in the neuron, I can calculate the gradient to know how much the output of the neuron is going to change. But now I need to know, if I change one thing in a neuron, how do I calculate the output of the network? Because like, it's not just you give me something different, I give you a different output. It's like, you give me something different, I'm going to take the output of the calculation I'm doing, I'm going to give it to all of these neurons ahead of me. They're going to do God knows what, and then whatever they did is going to result in the output of the network. So that is the big trick here, is to figure out how do I figure if I want to change the output of my network by -1, how do I trace the steps back so that I know what this one neuron has to change at the beginning of the chain? So that is the big trick. So to do that, we need to go to the basics here. So I have one neuron here, and this one neuron, whatever it outputs, is going to be the input for the next layer. So the first weight of every neuron in this layer is going to come from the output of this neuron. So if I have a second neuron in the layer, this is going to affect the second weight of everything on the next layer. You can follow me so far, right? So because I have this thing that the outputs of this layer are going to be the inputs of that layer, meaning that the weights on that layer that is ahead are going to come from the outputs of the layer before. And I'm repeating this 100 times just because it's important. And so remember that we had input layers, input gradients. So if we go all the way back here, I know that the gradient of my weight is my input. Conversely, the gradient of my input is my weight. So I know that if I change my input, it's going to change. I know how much it's going to change the output. And that's exactly what we're doing here, because I'm going to do something that is going to change the output of this neuron. In other words, I'm going to do something that is going to change the input of these neurons. So what do I need to do here? I need to take the input gradients of all the stuff in the layer above, and only the input gradients that were generated by this output. I'm going to repeat this part. This weight, this neuron is going to have an output. This output is going to be weight 1 on all of these guys ahead. Second neuron is going to be weight 2 on all of these guys ahead. So when I calculate the input gradient, I need to do the input gradient with respect to neuron 1, or if this were the second neuron in the layer, input gradients with respect to input 2, and so on. You all look like very 50-50 on whether this makes sense or not. So just to put this in a more understandable context, just imagine that you have an assembly line. I'm doing something, and then I have 5 colleagues ahead that are going to take the thing that I did and make some change on that. And whatever they do is going to be the output, the product. If I want to change the product, I need to know how much is the stuff my colleagues are going to do going to change what I'm going to do. So I know how to change what I'm doing. And by changing what I'm doing, my colleagues are going to do something slightly different. And then I'm going to get to the output that I want. So you need to think steps ahead. That's the thing that's difficult here. And the code is not going to make any sense because I can barely explain this in English. So let's look at the good parts first. So a network is a layer of is a slice of layers. We all understand that's perfectly good code. So please admire the effort here. To create a new network, I just create a bunch of layers, and when I create layers, it's going to create the neurons, etc. The amount of outputs of one layer needs to match the amount of inputs on the other layer. We saw that. So if it doesn't, then it gives me an error. The prediction we saw before. And finally, we have the gradients. So the gradients, I'm going to loop through all of my layers. Then I'm going to loop through all of my neurons. And then inside every neuron, I'm going to loop through every neuron on the next layer. and then I'm going to get the thing on the next layer that is affected by the thing on this layer. And there is some slicing magic here that is pretty ugly, and I should just rewrite this whole thing. Point being, at the end of the day, I'm going to have an updated value that I'm going to basically multiply this value in my list of gradients by whatever the new gradient was that came from all of this ugly mess. And so basically, I'm going to have gradients for, I'm going to note the gradient for this guy with respect to the output of the network. So I already knew how much changing the input something, I already knew how much changing something in this neuron was going to change the output of the neuron. But with these outputs, with these updates, now I'm going to know how much changing something in this neuron is going to affect the result of the network. So that's the whole point. Now I can make the whole thing learn. So I'm just going to run this. Just so we see the little graph here change, because, you know, it's cool. And, oh, I messed something up. Great. Let me just do some live debugging here. And, you know, it's not really live debugging. I just need to delete some stuff and pray. And did it? OK, let's see if this works now. So, you know, just making a plug for my employer, it's really cool, because when you screw something up, it tells you in red that, hey, you screwed something up. And so there you go, fun stuff. Let's see if it's going to work next time. And, oh, it did. OK, cool. No, it didn't. This is the old version. OK, let's pretend everything works, because it actually kind of looks the same. It's just a graph that goes like this. When you do it for the network, it takes a lot longer than just a single neuron, because, you know, you're calculating stuff for tons of neurons, not just one. The predictions are just as bad, because that bug from the layer implementation still applies to the network. My point is, you now know the basics of how a neural network should work. You know what neurons are, you know what gradients are. If you look more into neural networks, you're gonna see terms like feed forward, which is this process of taking the output of every neuron and using it as input for the next layer. You now know what backwards propagation is. Backwards propagation is this process of, you know, I take the input gradients here, and I use it to update the gradients here. And then I take the input gradients here, and I use to update the gradients here, so that I know how everything is going to affect the end result of the network, instead of just that one neuron in isolation. And basically, that is the basics. And writing the implementation is not so hard, except for the network gradients, which I should probably figure a better way of doing it. Thanks so much for being here. I'd like to say a big thanks to my friend and mentor, Francis Campoy, who helped me write this implementation and make the code kind of pretty, because it was pretty ugly before he came along. And big thanks to the organization of this event. Thanks to Renata, who's there and helped me make these slides pretty. And I'm forgetting one thing. Oh, yeah, and thank you for my employers for letting me come here. And if you need to make your Kubernetes development experience better, reach out to me. And that's it. Feel free to get in touch. Don't ask questions, because I'm not an expert in this. I'm going to be embarrassed, OK? So yeah, thank you.